Hey guys, it's Miss Fantassel. So I wanted to help you understand operations with radicals if you're having a hard time with this section on Canvas. And so the section starts out with number systems. And again, this is something that we covered in the beginning of the year as well. So you can check, if you brought your Math Nation books home, you can check in that first unit towards the end. You'll see where we talked about different types of numbers and different how to deal with radicals and roots and adding and subtracting them and simplifying them. So that would be just another resource that you can use. You can also go into Math Nation in your MyPass Connect and watch those videos as well if my video isn't helping you. So let's start with just what the different number types are. There's natural numbers. Natural numbers are like your counting numbers. What I mean by that is if you're beginning to count, like let's say I'm counting the number of students in class, I'm going to start counting with the number 1. So it starts 1, 2, 3, and it just continues, right? But you're not dealing with any decimals, you're not dealing with any fractions, it's just those whole numbers but starting at 1. The next is whole numbers. So whole numbers are very similar to natural numbers, there's just one difference. So whole numbers are going to be all of your natural numbers. So 1, 2, 3, 4, 5, all of those are whole numbers as well. But you're also including 0. So whole numbers, they start at 0 and they continue. So 1, 2, 3, 4. No negatives, no fractions, no decimals, just those counting numbers plus zeros, or plus 0, sorry. And then integers. So integers are also going to contain natural numbers, whole numbers, but now we're adding on one more layer. So with integers, it also includes negative numbers, but they still don't include any decimals or fractions. And so integers look like this. So like maybe -3, -2, -1, 0, 1, 2, 3. I'm going to put ... because they do continue. They go on forever. Rational numbers. Rational numbers, when you ever see the word rational in math, I want you to always think fraction. So rational expressions are expressions that deal with fractions. Rational numbers are numbers that deal with fractions. Rational exponents are exponents that deal with fractions. So rational numbers are going to include fractions. They're going to include decimals that end. So for example, like 0.25. It's going to include also decimals that repeat. So if you plug a number into your calculator and let's say you get like 0.333 repeating, that's going to be a rational number. And the reason why we call them rational numbers is because they can all be written as fractions. Like 0.333, you can write that as 1/3. 0.25 is 1/4, right? It's also going to include all of your integers because, for example, the number 2 can be written as 2/1. So that would also be a fraction. So it's going to include everything that we talked about above, but now it also includes fractions, decimals that end, and decimals that repeat. For irrational numbers, so irrational numbers are like the little oddball of the family. So irrational numbers, they're going to include decimals that do not end or repeat. And so that includes like square roots that don't simplify to a whole number. So like the square root of 2, the square root of 3, the square root of 5. Those are all irrational numbers. However, the square root of 4 we know is 2. And so that would not be included as an irrational number. That would actually be any of the other numbers above that we talked about. So square root of 2, square root of 3, pi is another big one that we see. And that's probably all we're going to cover for now. There are some more that are numbers that are used in math a lot, but you'll see those in a later course. So right now we're just going to focus on those square roots that don't simplify to a whole number, and pi would be our irrational numbers. And then real numbers are going to include everything above. All right, and so just to give you kind of a visual of how these number sets relate to each other. So I'm going to draw a nice big rectangle, and so this is like kind of like the universe. If you think about, that's like the universe of all numbers. So that's going to be our real numbers. And then real numbers are divided into either rational or irrational. If it's irrational, it's not going to go into the rational category, and vice versa. So they're very separate. It's kind of like if you're thinking about real numbers as the universe, rational numbers would be like Earth, and irrational numbers would be like Mars. They don't connect. Like they're not, they don't overlap at all. So rationals, irrationals. And then inside rationals, we have integers. Okay, and so integers would be like, I don't know, the United States, right? So we have real numbers as universe, rational numbers are Earth, irrational numbers are like Mars, so they're separate, and then the United States would be like integers. So the United States is inside of the Earth, and the Earth is inside of the universe, but they're not like it just because it's on Earth. So for example, the square root of 2. The square root of 2 would fall into rationals, but it wouldn't fall into integers. Whereas 4 would be an integer, it would be a rational number, it would be a real number. Kind of like you live in the United States, and you also live in the Earth, and you also live in our universe, right? So then the next number set would be, let's see, whole numbers. And then the last one, natural numbers. And so this is just a nice graphic of how all of these, and I'm actually going to erase 4 because 4 would be inside all of them. So that would really be like here. And so that's how all of these different number sets relate to each other. So adding rational numbers. When you're adding rational numbers, so now remember rational, think of fraction. So, I don't know, 1/3 plus 1/2. We want to make sure we have a common denominator. And then we want to add the numerator and keep the denominator. So I'm going to try to think of a number that 3 and 2 can both multiply to give me. Whenever I'm doing this, I always start kind of with the bigger number, and I'll just count by that number until I find a number that can be divided by both 3 and 2. So I'm going to start with 3. 3 is not divisible by 2, so I'm going to keep going. So 6 is divisible by 3 and 2, so that's going to be my common denominator. And so in order to make my denominator equal to 6, for 1/3, I would have to multiply by 2. Make sure that you're not just multiplying to the bottom. We also want to multiply to the top because we don't want to change the value of our fraction. So if we look, we're really just 2 over 2 is really just 1, so we're really just multiplying by 1, so we're not changing the value. So it's really important that you're multiplying both to the top and the bottom of that fraction. And so we have 2/6 plus 3/6 and we add our numerator, so that would give us 5/6. For multiplying rational numbers, so let's say I had 1/3, and we did talk about this in the video that I posted yesterday as well, but this is just a nice little refresher for us. So whenever we're multiplying rational numbers, we multiply straight across. So in that case, we don't need a common denominator. And so we end up with 1 over 6. Okay, adding rational and irrational numbers. So with adding rational and irrational numbers, it's very similar to adding like terms. So for example, a rational number, I'm just going to pick one, like 5. And then an irrational number, we'll go with the square root of 3. And so 5 and the square root of 3, they're not like terms. They don't have like radicals with them. This one doesn't have a radical at all. So you really can't simplify this down any further than what it is. So it would just be written as 5 plus the square root of 3. Just like if I had 5 plus x, those are not like terms, so I would have to keep it as just 5 plus x. Multiplying with rational and irrational, so I'm going to use the same example. So 5 and then times the square root of 3. And then so for multiplying rational and irrational, I'm just going to kind of keep them next to each other. You can't multiply inside that square root if the number is not also inside the square root. So I just would write it as 5 square root 3. Just like if I had 5 times x, I would write it as 5x. So if you see a number in front of the square root without an operation with it, it's multiplying, okay? Simplifying radicals. This is something I also went over in my last video, but I'm going to go over it in a little more detail this time. So the square root of 50. We talked about in the last video that the first thing you want to do is identify your index, which is that little number that goes right here. If there isn't already a number, it's automatically a 2. So this is a square root. So I'm going to go ahead and just fill that in. That number is going to help me when I'm simplifying. And so my next step is to take the number that's inside of our radical and break it all the way down to prime numbers with a factor tree. So 50, I could use 2 and 25. I could use 5 and 10. It doesn't matter. You'll end up with the same thing in the end. So just pick one, whatever you see first. So I like 5 and 10. Okay, 5 is a prime number, so I'm going to go ahead and circle it. But 10 I can break down a little bit further. So 2 times 5. 2 is a prime number, and 5 is a prime number. And so 50 is equal to 2 times 5 times 5. Now, when I'm moving my number outside of the square root, that index, so this number that I wrote right here, that tells me how many I need in each group before my group can move outside of the radical. So I'm looking for pairs of the same number. I have a pair of 5s. So that 5 is going to go outside, but I'm only going to write the group once, okay? So each group that you circle, it only gets written outside one time. And then whatever is left over stays inside. So this little guy right here, this 2, he doesn't have a buddy, so he's going to stay inside. He doesn't get to go to the bathroom because he doesn't have a buddy to walk with. Okay. So then for our next one, we have 32. And so the number that goes into 32 would be 4 and 8. 4 can be broken down further. So 2 and 2. And 2 is a prime number, so circling those. 8 can be broken down into 2 and 4. 2 is a prime number. And then 2 and 2. So 32 can be written as 2 times 2 times 2 times 2 times 2. And again, I'm just going to circle my groups. So right here tells me that I'm looking for pairs of the same number. So I have a pair of 2's here. So that pair is going to go outside. Then I have another pair of 2's. So that second pair is also going to go outside, and I'm going to always multiply them together. And then this 2, he doesn't have a buddy, so he has to stay in. Poor guy. And 2 times 2 is 4. I bet we're all feeling like that. Poor little 2 right now. None of us can go outside. All right. So here's the big one. So 1260. Again, there's no little index, so it's automatically a 2. And I know that it ends in a 0, so definitely 10 goes into 1260. So 10 times 126. 10 I can break down to 2 and 5. 2 is a prime number and 5 is a prime number. 126 can be broken down by 3. So 126 divided by 3 would give us 42. So 3 and 42. 3 is a prime number. And 42 I can break down further as well. So 42 is 6 and 7. 7's a prime number. And then 2 and 3. So I like to put them in order just so I keep it consistent, but 2 times 2 times 3 times 3 times 5 times 7. I'm going to circle my pairs. So I have a pair of 2's and a pair of 3's. So my pair of 2's comes outside. My pair of 3's comes outside. And then 5 has to stay in. He doesn't have a buddy, and neither does 7. And so 2 times 3 is 6. And 5 times 7 is 35. So 1260 simplified would be 6 square root 35. All right, and so how can this help us? And so the next topic we're going to look at is adding and subtracting radicals. So just like when you're adding and subtracting like terms, you can combine like terms. You can only combine like radicals. So what I mean when I say like radicals is it has to have the same index and the same radicand, which is the inside. If you don't have a number in front of your radical, then it's automatically a 1, just like with a parentheses. So for this one, I'm going to just add the 2 plus 1, which is 3, and keep my like radical. Just like if I had 2x plus 1x, that would be 3x. It's the same concept. So you're just really replacing x with the square root of 3. That's how you're going to treat it. For the right side, so now we're looking at this one. Notice that I don't have like radicals. Square root of 3 and square root of 5 do not have the same insides. So this cannot be simplified any further than what it is. So simplified would just be 4 square root of 3 plus 2 square root of 5. You cannot simplify that further. Sometimes they'll try to trick you. So in this next example, when we're looking at it, the way that it is right now, we don't have like radicals. However, sometimes you can simplify it to make them have like radicals. So you want to make sure that you're always simplifying and checking before you check to see if you can simplify or not. So I'm going to start with simplifying the square root of 32. We already did that in a previous problem, so I'm just going to kind of run through it quickly, but we have 8 and 4. 8 is 2 and 4. Circle our 2, 2 and 2. Circle, 2 and 2, circle. So 2 times 2 times 2 times 2 times 2. I have a pair of 2's. Another pair of 2's. So 2 times 2 and then that one stays in. So the square root of 32 can be written as 4 square root 2. Now we're going to do the same thing with the square root of 8. So we have 2 times 4 and 2 times 2. Okay, and then we have a pair of 2's. He goes outside, and then this little guy stays in. So square root of 8 is the same thing as 2 square root 2. So I'm going to bring that down, replace it. And then our last guy over here, our minus or our negative square root of 2, he can't be simplified any further. So I'm just going to bring him down, but I am going to put a 1 in front, just so that I remember that there is a number there. And so then to simplify this, now I have all my like radicals, so I can just add or subtract the front. So 4 minus 1, so 6, 5, so 5 square root 2. Multiplying with radicals is a little bit different than adding and subtracting. So when you're multiplying with radicals, you don't have to have like radicals. Just like you don't have to have a common denominator when you're multiplying with radical, or when you're multiplying with rational numbers. So with these, you're just going to multiply insides with insides and outsides with outsides. Okay. So that means I'm going to multiply 4, or sorry, not 4, I don't know what I'm even looking at, 2 times 5, and then square root 3 times 3. And 2 times 5 is 10, 3 times 3 is 9. But look, if I look back at the breakdown, I have a pair of 3's. So we know that the square root of 9 is just going to be 3. So that's 10 times 3, which is 30. For problems like the next example, so we have our parentheses. We've used the distributive property a ton, so you guys should all be familiar with the distributive property. It works the same way with radicals. So I still need to, if you think about the word distribute means to share. So it's like I'm sharing this number in front with all of the numbers in my parentheses. So I'm going to multiply to each one of those. So 2 times the square root of 3, I'm multiplying to an outside. So that's going to be 2 times 5 on the outside. Plus my second time I'm multiplying. So now when I'm multiplying to the square root of 3, I'm going to multiply an inside. So insides with insides. So 2 times square root 3 times 3. And 2 times 5 we know is 10. So 10 square root 3 plus 2 square root 9. And we already said that the square root of 9 is 3. So that's 10 square root 3 plus 2 times 3, which is 10 square root 3 plus 6. All right, well, that's it for today's lesson, guys. So I hope that this helped clear up any misconceptions that you may have had, and don't forget to reach out to any of your teachers if you need more support. And I hope that you guys are staying safe, healthy, and have a good rest of your day.